We've been drawing things with arrows to find resultants, and we've been talking about equilibrium. And I would like to get clear on the difference between just finding a resultant and looking at some forces that are in equilibrium. If you just have three forces, for example, and you want to find the resultant, you can arrange those three forces tip to tail, and what you would probably do is in CAD, you would take a copy of those forces and stick them together. Here's the start of those three, there's the end of those three. And to find the resultant, you start at the start of the tip to tail, and you head off to the end of the tip to tail, and there is the resultant with its magnitude and its direction. Now, for every force there is an equal and opposite reaction. So with these three forces pulling on this I, this bracket, there are equal and opposite reactions pulling in the opposite direction so that it won't pull out of the wall. And all of those forces and reactions are equal and opposite, and they add up to 0. If you took each force and each equal and opposite reaction, and in any order you want, strung them together tip to tail, doesn't matter what order, take all those forces and all those equal and opposite reactions and arrange them tip to tail, you will get a closed loop. There won't be a big gap like there is when you look for a resultant. It's a closed loop. If you want to think about finding the resultant, you could think about it this way. If you start at the start point and head off to the end point, the distance from the start to the end is 0. The resultant is 0, which is another way of saying all these forces and reactions form a closed loop. And we know that all the forces add up to 0. Therefore, this set of forces and reactions is in equilibrium. And if you were just looking at that bracket, how would you know it was in equilibrium? Because it is not moving. Therefore, all the forces add up to 0. And here are our three equilibrium equations, the tools in our toolbox. So we know all the forces in every direction must add up to 0, and all the moments around any point in any direction must add up to 0. Equilibrium equations. And that is related to the idea of Newton's third law of motion. For every action, there's an equal and opposite reaction. For every force, there are equal and opposite reactions. Going back to our red wagon again, where we started the term. First, we had the two kids pulling out in front of the wagon, and we wanted to find the resultant of those two kids, the net result of those two pulls. And we found the resultant this way. We had a couple of approaches. We tried it with a parallelogram, and then we tried it with a tip to tail, and we got the same result, the same answer. So the net result of those two kids pulling out in these directions was one resultant pulling out at 14.14 pounds straight ahead. Then we imagined another situation where those kids are still doing that, but then a third kid hooks a rope to the back of the wagon and pulls in an equal and opposite direction with equal and opposite force. So he or she is pulling with 14.14 pounds of pull. And what we wind up with there is a wagon that is in equilibrium. It is not moving because the sum of all the forces in the x direction add up to 0. So that thing is not moving, it's in equilibrium. Here's our bracket with one force pulling on it. There's an equal and opposite force pulling the opposite direction. And if you want to think about a resultant, the resultant is 0. You start at the start point, you end at the end point, which is the same point. The length of that resultant is 0. In other words, those two arrows add up to 0. It forms a closed loop. Now, that one force at an angle, you could split that into an x component and a y component if you wanted to, and we often do that when we're using a calculator instead of CAD. So here are the x and y components of that slopey force. If you put the x and y components tip to tail, you'll notice they do not form a closed loop. There's open space here. So we are not yet in equilibrium because we don't have equal and opposite reactions yet. And backing up here, so here's our original slopey force. So our original slopey force has an equal and opposite slopey reaction. And I took the x component and the y component and the equal and opposite slopey reaction, and I stuck them together tip to tail. Now we have a closed loop. So what we see here is those forces and the equal and opposite reaction together form a closed loop and are in equilibrium. If you wanted to, you could take that slopey equal and opposite reaction and you could find the x component and the y component of that reaction. So then you could draw a diagram of that system with an x component and a y component of the force and an x component and a y component of the reaction. And you could take those components, the x and the y, and string them together tip to tail. And what do you get now? You get a closed loop. So that bunch of forces and reactions are in equilibrium. Just to review one more time, if we have just the forces and we put them together tip to tail, we could find the resultant, the one net result that gives the same effect as those three forces. And we do that by starting at the start point, heading off to the end point, and that arrow is the resultant, the one force that has the same net result as the three smaller forces. But if we take the forces and their reactions, the forces and their reactions, the forces and their reactions, and we put all the forces and all the reactions together, tip to tail, they form a closed loop. In other words, the resultant is 0. In other words, all the forces in the x and y direction or in the slopey direction, all the forces add up to 0, and this thing is in equilibrium.